Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our webinar today, Retaining Wall Design with Sleepers and Panels. My name is Megan Purdy and I will be your host for today. In keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognise their continuing connection to land, waters, skies and community. We recognise Aboriginal and Torres Strait Islander peoples as the oldest continuous culture on Earth and our first engineers. We pay our respect to them and their cultures and to elders past and present. Before we get started, I'd like to acknowledge that today's event is being hosted with Engineers Australia's industry partner, Brickworks. Brickworks is recognised globally as a leading manufacturer of quality building products, including bricks, blocks, retaining walls, pavers, natural stone, wall cladding, facade systems, roofing, and so much more. Their brands continue to build their reputation for delivering quality, and they lead the industry through style and product innovation, creating impressive materials designed for inspiring built environments. We thank Brickworks for their continued support. Now today we'll hear from two speakers followed by our live audience Q&A, and I encourage you all to please send your questions through to our speakers via the chat box. I now would like to take the opportunity to introduce our first speaker, Dr. Bert Look, Senior Principal, FSG, Geotechnics and Foundations. Bert has over 40 years professional engineering experience and is widely recognised in the areas of earthworks, expensive plays, landslides, ground improvement, risk assessment, value engineering and site characterisation. Bert is the 2014 Queensland Professional Engineer of the Year and the AGS Practitioner 2018. Bert was also awarded the Medal of the Order of Australia in 2020 and has published 4 books and over 95 technical papers focused on industry practice developments. His latest book is Earthworks, Theory to Practice, Design and Construction. This is based on earthworks, course notes and feedback from practicing engineers. Please join me in welcoming Dr. Bert Look.
Thank you all for attending, and good afternoon to everyone from different parts of Australia or elsewhere. I'm going to be talking about retaining walls, designing with sleepers and panels, and illustrating that with some case studies. The format of this is really more trying to give you key principles rather than going through any specific details in any aspects. So my name is Bert Look. I'm basically a consultant, semi-retired, but I do a lot of training, value engineering, and review sort of related work for legals and insurance companies. So some of these are sort of using that to illustrate things that do happen or go wrong, as well as things that do go right. So this is our roadmap, which we will be following. We will be looking at the wall analysis and design, then wall pressures in a general sense for most that will apply to most walls. But this talk is meant to be specific to sleeper walls. I will illustrate that with case studies, but I need to ensure that people have key principles of analysis and designs and wall pressures before moving to the specificity of this type of wall. We first must look at wall stability checks. This can be global, external, and internal, as well as serviceability checks. Now, these are a generic sort of checks required, and for sleeper walls, for instance, you may not need a bearing stability check for this particular wall, and specificity of other walls may occur. But these are sort of general checks that one is expected to have done. The various analytical methods shown do vary with the type of project and how detailed you need to go. Now, the Rankine and Coulomb are the key concepts taught at university, so everyone would have covered that. I'm not going to cover such theory in details. Rankine is considered a lower bound, and Coulomb is an upper bound, which considers wall friction. Now, has been an advancement with that at Cackett and Carousel, which may or may not be taught at certain universities. I will illustrate that in slides to come. But that is the best represents the current theory and practice. Keep in mind, Rankine and Coulomb were a few hundred years ago, And so I guess it's updating the theory, not superseding, just updating some aspects of it. And then Tasagi came up with certain earth pressure envelopes, apparent pressure envelopes, which allowed for observation in practice, which again the founding Rankine and Coulomb did not have. And so he allowed for arching and for braced cuts what would occur. There are other types of analysis, limit equilibrium, for instance, and that does cover global stability, but it also covers if it's a sloping and varying ground condition, as well as multi-tiered stepped walls, for instance. And then, of course, we have the finite element analysis, which goes into a fair amount of detail. It will cover construction sequencing, the wall rigidity, as well as give you idea on the displacement. So all of these are various methods. For smaller projects, you would tend to use the ones to the left and certainly not the FEA. The apparent pressure distribution, I will illustrate that in slides to come, but it moves away from the triangular theory that is all part of Rankine-Coulomb that is taught at university. These are the standards that applies to retaining walls. There is AS 4678 and AS 5100. Now, these standards are a little dated and they have slightly different approaches. The AS 4678 factors the resistance, R star, and also factors the action. And so we have R star greater than equal to S star for the stability. AS 5100 takes a bit of a different approach, unfactored, but then applies a geotechnical strength reduction factor later on, a 5G factor. Now, the interesting part of this is that there is no post and sleeper aspects within these retaining walls. So while we have codes which are dated, this talk is about post and sleeper retaining walls, and you will not see that explicitly addressed in these codes. So that leaves us a bit of a quandary where the concepts and still apply, but there are subtleties that apply to certain types of walls and is not covered within these standards. So in an overview sense, you either build up a wall or place a wall while you're excavating, which is the top one. Now the gravity wall, it's typically a backfill, and the excavation where you put sheet piles and various, you could soil nail, for instance, and have a list of other types of walls there that can be used for the excavation type. Now, the king post and soda wall, which is the subject of this talk, a sleeper wall, can apply to both. The others can't, or more difficult to apply. So the sleeper walls do encompass both backfilling to actually keep much of that land for development, and so you have a larger sellable development area as or area that's usable, and that's what a wall is used for. Now, the benefits of this wall is it's narrow and it takes up little space, so it can be installed close to the side boundary, and that slimness is a key benefit, whether it's excavation or building up. Now, I've shown something here by O'Rourke and Jones going back 1990, and I've circled the gravity walls. The reason I'm doing that is because that's the anchor point for Coulomb and Rankine. And as you notice, there are 24 other types of walls since then. So 200 years later, yes, there's been a lot of development, but we are taught something from 200 years ago, so we need to just advance ourselves a bit more than that. And I think it's essential to cover some of the nuances that have the aspects that have changed since that time. So Rankine and Coulomb dealt with gravity walls and not any of the others. And that's how their theory was covered. So let's take that in a little more detail before I go into some case studies. Let's look at the soda pile wall, which is specific to this talk and which is the key focal point. So everything is really defined by that wall height, which gives us the active zone. And then there's arching between the posts, and then we put a lagging, which can be shotcrete, wood, concrete, steel sheeting. But that H is a key input as well as the soil condition. And typically, we would put a minimum surcharge of 10 kPa to account for extra loading unaccounted for, or even surcharge construction equipment. Now, below that, based on H, we'll define for a design what is the pile width and what's its depth. So those are the design elements which we have to get right. And typically, they're 1.5 to 3 meters apart, but that does depend on soil type. The analysis method uses something called Brom's method, and depends on whether it's a clay or granular material. We have slightly different approaches. But basically, you neglect the first 1.5 B for cohesive soils. This is the undrained analysis, and for the effective stress analysis, which applies to drain conditions and clay in the long term, we neglect the top B. So that's one of the key elements of design. Then we can install it through drilled, and it could be H-piles, double channels, pipes, or concrete. Now, one of the aspects that we have to consider is something that's unique to Australia that I'll come to. So you see the actual UBCs piles that are installed below the ground, and then the uprights, and then the panels between those uprights. But a key element that is probably more unique to Australia to some extent, not completely though, is the fact that we have a lot of expansive soils. Roughly 1/3 of the country is covered with that. And that active zone does vary from 1.5 to 4 meters in the arid regions. But for most purposes, it's around the 2 meter mark. Now, half of that will be a cracked zone. And in that cracked zone, because of the seasonal variation, things, when soils get wet, they swell, and when they dry, they shrink away. And if they shrink away, they lose contact with the actual pile that's in the ground. So therefore, we are losing passive pressure, and that needs to be considered. Also, to give it a bit of future proofing, we should also design for at least 0.5 meter of future excavation in front, or 10% of the height, whichever is larger. That could be because of someone digging a trench or a service line or a pipe, for instance. So it's really try to future-proof your design, and that's a key consideration as well. Now let's just illustrate how the soil conditions or future-proofing does affect things. So here's an example of next to the water where things have gone wrong, as you see on the photos on the left. Now, it would have been, these are timber piles in this case. So the timber piles are there. You have an active pressure and a passive pressure. And then a flood occurs, for instance, and there is erosion. And soil disappears. So it's no longer the actual full height, and now it reduces to a different height. And so the passive pressure in front, which is the resistant part, is different and smaller. So one has to consider not what the existing ground is now, but what the future ground is. And no more is it more critical than in any water-based systems. But unlikely that most people will deal with the water-based one, but it illustrates the key point I'm referring to, because in this case, without doing that, it results in overturning. So this is the soil pressure that occurs between the panels at the top. In plan, you can see this is sleeper, and then there's this pressure over this length 2L. And the lower diagram shows for sleeper walls the passive pressure that occurs at the base, and then that active pressure at the top. Now, that is for sleeper walls, not for continuous walls. For continuous walls, the pressures are a bit different. As you can see on the right, the active pressure extends to the full depth, while the passive pressure extends from the ground level. And again, keeping in mind, we have to allow for changing ground levels in the design. Now let's see how the soil conditions can affect things. So here's an illustration of where medium dense sand, 4 meter high above ground king post, and then below ground 2.5 meters in a very stiff clay. And we've put a nominal 10 kPa surcharge at the top, and we see adequacy and strength in this particular analysis. It's called a safety factor, if you wish, 1.1, which means it's just nominally adequate. As we see, it deforms. And what you're seeing is the sort of Rankine planar surface. Now, the difference between Rankine and Coulomb is actually, one is Rankine is planar, while Coulomb is a log spiral failure surface. But so what we're seeing is how the wall will deform for this particular ground condition. Now, let's now look at a different condition where the medium dense sand is throughout the entire profile. And we see that the adequacy and strength drops to 0.98. So it's below 1, so unacceptable. But you notice in front of the wall how it's pushing up. And that's a failure that's occurring because the pressure has exceeded the strength of the soil. So this illustrates how everything else being the same, except the medium dense sand, in this case, is failing. And before, we had a very stiff clay within the analysis. So let's just look at now what Australian standards would have told us. And on the left, you see the nice triangle distributions, which you're accustomed to for active zone and passive pressure. And there's a larger triangle for the at-rest condition. Now, if we look to the right, we'll see this is for us a restraint condition. Now, the interesting thing in this is that the Australian standard buries this in the appendix. But for the at-rest restraint, you know it's an you notice that at-rest restraint, and that could occur, for instance, when they say restraint is, it could be, for instance, if it's on a pile foundation, or is it on hard rock. Therefore, it can't move, it can't deform to be active, so it's at rest. So if it's at rest, the at rest K0 value applies. And if it's strutted or restrained at the top, it moves away from a triangle to that half ellipse that is shown there, or that lower one squiggly ones, which is the apparent earth pressure according to Sagi. So this is actually in the codes from 20 years ago plus, that is not necessarily triangle. And this is the issue with Rankine earth pressure theory. So we have this history timeline, which I've covered, but just to summarize, Coulomb was first, and they had a wall friction, much more complicated. Rankine simplified it with the active earth pressure Ka, which is 1 minus sine phi divided by 1 plus sine phi. But as you notice, these 1776 and 1857. So fast forward now, almost 100 years later, Tersaghi has what he called the fallacy of earth pressure, because he showed the apparent earth pressure from observation. Rankine and Coulomb, they were more of the theoretical mathematician sides, and they didn't actually have the benefit of the monitoring and observation that we have in current system. And then we see Caruthers 1948, and that should be the earth pressures we're using, not the ones from 200 years ago. I asked a survey in 2016 how many people just use Rankine, and it seems that 42%, almost half of people, just use Rankine. So sad to say, that is a bit out of date. As you notice, 1857 at Rankine, and Rankine, as I mentioned, is a lower bound. So let's just explore the differences now over the next 3 to 4 slides before we get into some more details of some sleepers and king posts. Let's take you back 60 plus years. How would you have done in this exam? This is an exam at Harvard University. Everyone would have heard about Casagrande, and he's asking a question in 1962, before I'm sure a lot of you were born. What is the basic weakness of the classical earth pressure theories when applied to many types of modern structures? And the question below is very similar about the assumptions of Coulomb's earth pressure theory. And really that leads to the fact of arching, and it's not triangle. And I illustrated that in the Australian standards with the way it's not necessarily a triangular. And he found that the point of application is not the 1/3, from as per the triangle centroid, which is nice, simple. And again, keep in mind, this is all to do with back in that day, they didn't have a calculator or even a slide rule. So things had to be simple. And that's what was very good out of Rankine. It can be simply applied. And that is why it became the foundation of our NASA. It does not mean it applies exactly like that when we have better computational power at our disposal in current days. So Tasagi had a bit of quarrel with the U.S. Bureau of Public Roads, you might say, and you would see Tasagi highlighted the fallacy. He called it fallacy of pressure, but really it's because it wasn't the triangle distribution, and he was now observing conditions, and this is really more for braced excavation. So you see how things are changing, and we need to be careful about blindly applying the established and certainly the key one that is taught at the University of Rankine Coulomb. So Rankine represents more of a lower bound solution. If you use it, yes, you'll be conservative. And yes, you're spending more money than you should because it's conservative. Coulomb is closer to the mark, but it has a bit of a bug at friction angles greater than 35 degrees. And Cackett and Kersel in the 1960s looked at that. So you just compare that over the next few slides. And here we have the active pressure coefficient. As you can see, based on the actual wall friction, as well as the friction angle of the soil, what would be the Ka? And the lines aren't too far different. Coulomb overlaps with Cackett and Kersel, while Rankine is just slightly to the side of it. So 10% error in scheme of life, that is very minor to have a 10% error, and that's the active earth pressure coefficient aspects. But if it was that alone, then all will be good. But when it comes to the passive pressure, we see things are a bit different, and Rankine underestimates by 100%. So that's a huge overdesign and a huge cost to many projects if we keep on using Rankine. Coulomb is closer to the mark for the Cackett and Kersel, which is, as I said, the benchmark that we should be using now. But the issue with Coulomb is that once it crosses 35 degrees, there it begins to have an error. So we should limit it to that about that. It overestimates it by about 20%, and therefore we are using up our factors of safety. So let's move on from the theoretical aspects, which I've covered, and we need to see the physicality of what occurs. Now, when construction occurs, people park vehicles. You can see there's a retaining wall being built, in this case, a reinforced wall or structure, and you can see people park their vehicles behind. They shouldn't, but they are. And that's what happens on construction sites. And you see a roller there, a 17-ton roller being placed here, which leads to the fact that when you build up a wall, often you compact behind it. And when you do, and you have a roller, certainly, hopefully not that roller shown there compacted, and you have a small roller, it creates an earth pressure on the system. So what we're seeing here is the active earth pressure for a nominal Ka of 0.3. And we see it's 18 or 30 kPa. Now, the act of compacting it, you want to compact it to drive up your friction angle, but in so doing, the conundrum here is that you are applying a passive pressure. The soil is being pushed into the wall, so that's a passive pressure. And you notice that part which shows earth pressure due to compaction, that's the Kp value versus the Ka which you designed to. So that's an overload of the system for a certain height. And what we see at various compaction equipment, this occurs, the heavier the equipment, the greater the pressure. And if you look at some of those pressures, even for a 10-ton roller, and it should be less than that, we should be thinking of small vibratory plate behind a wall. We are seeing 12 to 20 kPa. So what in essence is saying is that if you had a 3-meter wall, it's almost like having an extra 2+ meters of soil pressure simply by compacting behind the wall. So we need to be careful here of saying we want high friction angles. High friction angles means compacting. Compacting means higher pressures, and you have to allow for compaction-induced pressures. So that's another key design element that we need to consider. So let's now look at a global stability issue. And what you could see there is the wall, a sleeper wall, and you can see the picture above, there's a failure, and 0.98 represents the global stability that has occurred. The global stability failure. The wall itself was designed properly, so it's ironic to say it's a well-designed wall, but it didn't check the external stability, and what we are seeing here is a result of that, a bigger failure beyond the active pressure or the compaction pressure or any other pressure. You're now dealing with the global stability analysis. And that house, the services broke, how it had to be abandoned because of that failure surface. What you should see to the bottom is that watermark near the lower end at around 35 meters, 35 to 67 on the far right of the screen. So that's water there from a creek. And what is occurring, that creek is providing erosion in that area. So 25 meters away, that erosion moves soil away, and therefore the soil moves in that global stability, and that passive pressure in front of the wall is being lost. And therefore the passive pressure that they thought was there no longer exists, and it's the bigger issue is the global stability of the wall, and it's not the wall pressures per se. And failure results. Now we come to another type of incident that occurs. And this one was about 20 years ago plus. And what we see is a bridge abutment for a rail line, in this case, to a mine site. And there was some movement of the shotcrete face when the wall moved. So I was asked to look at this. And the passive pressure should be the full depth of the soil, but I mentioned about the loss of contact when soils shrink away and when they're expansive soils. And that represents the dashed lines at the top represent the full passive pressure, but now that passive pressure is being reduced because the contact with the actual embedded part of the post is being lost for that shrinkage zone, and therefore when that moves, in the shotcrete face cracked. So it wasn't ultimate failure as was illustrated before. This is more serviceability failure, where we notice some cracks occurring because of that shrinkage occurring. And here's another case of from say 20 years ago, roughly, where these are the drawings shown, and it's stamped approved by council. So it's approved drawing. And you will see in the drawing there are two 1 meter high stepped sleeper retaining walls. So it's been built up for 1 meter in each case to the actual final level. And they needed to build that up because this is a flood prone area, and therefore you needed to build up some height above that flood level. But in the drawing, in the notes, to have that work, it said you need 100 kPa. So they needed to improve the ground with surcharging and ground improvement over a year of surcharging. And what I've highlighted, the circular part, it says, but a slip-stability analysis has not been conducted on the wall. That was approved by council. So approval by council doesn't mean they've checked that level of detail. And what happened is there's a little subtlety here that those who have eagle eyes would have seen that little circle. That is a sewer pipe, 1 meter from the boundary. So into the other land, which is waterlogged, there is a pipe, and roughly 1 meter from the boundary. And failure occurs. So what you're seeing is actually where the surcharge has been removed for fair distance. That's what you're seeing. It's still there to the back, but in the middle of the photo, you're actually seeing where the surcharge has already been removed once the failure occurred. And the water you're seeing there is a lot of sewer water running into mangrove area. Obviously, that's not what anyone would have liked. So it was a matter of understanding that sometimes the boundaries of our wall extend beyond our site, And in this case, yes, it affected our site, but it affected a lot of other people. And in this case, an environmental harm was done. So what happened? There was unloading from the top by an excavator, which couldn't enter the wetlands. So it's removing the soil at the toe, so therefore making it weaker to create that failure surface in red shown there, while it's loading it at the top. So that's how it's been removed. And you can see where those two pipes are, and the actual boundary is just inside there, where the ground had improved, yes, and that's where the two sleeper walls were to be constructed. So these subtleties prior to the wall even being placed and the ground improvement occurring led to this failure even before the king post and so the actual sleeper wall was being installed. So as you notice, it would now have to be redesigned and not that 1 meter tiered system that was shown on the drawing. So we have ruptured pipes that extended roughly 50 meters from the central area, and yes, that affected the wetlands. There is some analysis, so you can see the elastic plastic analysis. Again, I'm saying this is 20 years ago, but you can see the deformation and the movement of 0.55 meter would have occurred from the loading and the soft ground condition below to push that pipe. So the pipe being able to be displaced half a meter is obviously unrealistic, but that's what would have occurred certainly from this analysis. Okay, a last case study. We are all handymen. We like to do things around the house, and we might build a sleeper wall. So in this case, this is a timber structure. We've put some timber in front and some panels across and install it. So you see the top view, and then to the far right is the front view where it has failed. This is just a garden just below road level. And what was done now, this is actually a friend of mine. He had bought this house, and 5 years after he bought it, this is what occurred. The wall itself was at least 20 years, possibly 25 years old. So it shows that these particular type of walls, in this case a wooden sleeper wall, would have a limited design life. And that's because of blocked weep holes, no concrete base. It was just installed in the ground, and you can see the degradation in the lower right photo. And this would have occurred because of the high moisture content for no weep holes. There's an abundant, if there's fungi, and that could also degrade the wood, as well as if there's a soil pH. And also in high temperatures, certainly in warm climates, if the ground is 15 to 35, in cooler climates, probably less so. But all of these can occur if it's a wooden system. So yes, we like to do our handiwork, and these are an example of the sleeper walls and panels, in this case using wood, but it has a limited design life. So what we need to be aware of here is that if we have to go to a longer design life, we need to be using, for developments, for instance, concrete, steel, to take care of that. So I have covered some key aspects of sleeper walls and the panels that are used, as we can see in that diagram. This guy here was a very strong advocate in his first term elections about building walls. So it doesn't get any better than this. And he, was very vocal in it, shouting out about building a wall. But one needs to check for global stability as well as ultimate serviceability conditions, and he probably didn't mention that aspect. So I hope you have got something of an overview of walls, and specifically about sleeper walls. And yes, they can be cost efficient and save valuable real estate and land because it doesn't take up much space, but one has to be aware of certain other factors as well. Thank you for listening.
Thank you, Bert, for your input today. I now have the pleasure of welcoming our second speaker, Adam Ransley, Landscaping and Civil Manager at Brickworks. Adam has a strong foundation in mining and civil construction, and he brings extensive industry experience to his role at Brickworks, Australia's leading brick manufacturer. He is committed to the company's forward-thinking approach and takes pride in Brickworks' ongoing commitment to strengthen Australia's building industry. Please join me in welcoming Adam Ransley.
Thanks all. Thanks for the introduction and appreciate being here today. I'm Adam and I am the Landscaping and Civil Manager at Brickworks Building Products. And some of the things I'm here to talk today about are some case studies, the zone of influence, minimum embedment, quality products, why Brickworks, and our range. So the first topic I would like to discuss today is common issues observed with concrete sleepers retaining walls. Whilst concrete sleepers offer numerous advantages over alternate products, problems can arise if they are not installed correctly, if substandard materials are supplied, or ongoing construction around the walls. These issues can result in both significant delays and costly rectification works. So case study 1, creepage. When installing individual concrete sleepers, there is an increased risk of height creep due to inherent products tolerances and variations in installation procedures. The image highlights the difference between a panel installation and a single sleeper installation. The panel system shown on the left requires only one individual lift, compared to 5 lifts for the single sleeper system. As a result, the panel system requires only one level alignment rather than multiple adjustments, delivering significant time and cost savings for the installer. Case study 2 is growth. When installing individual concrete sleepers, incorrect installation of geofabric can have an increased risk of the vegetation growth through the wall. This can be visually unappealing for the end user and may also lead to further issues, including post-installation sleeper movement and silt runoff down the face of the wall, where a panel system eliminates that risk. Case study 3. As retaining walls are typically among the first activities undertaken on major projects, a 2 metre by 1 metre panel, each equivalent to 5 single sleepers, provides significant advantages in terms of installation time and labour efficiency. These efficiencies translate directly into measurable benefits for the customer's project schedule and overall budget. Furthermore, reducing the installation by 5 individual lifts also eliminates 5 potential pinch points for risk on site. With WH&S remaining the highest priority, panel systems offer a safer and more efficient solution for our installers. When installing multiple individual sleepers, bowing can develop over time due to uneven load distribution across the wall. Panel systems distribute loads across a significantly larger surface area, reducing point loading and minimizing the risk of wall dislocation. Since the introduction of panel systems, Brickworks has recorded an 80% reduction in complaints related to bowing-related retaining walls. While AS 3600 specifies that the structural design of concrete sleepers is based on a maximum allowable deflection of span divided by 250, where the span is defined as a distance between post centers, the level of deflection is often visibly undesirable. The comparison shown highlights the difference in deflection between a traditional sleeper system and a panel system. The panel is delivering a noticeably straighter and more visually appealing outcome. Case study 5, zone of influence. As you can see in that photo, there is machinery on a wall being used behind the concrete sleeper system. Quality issues do not arise solely during the construction phase. As retaining walls are typically among the first elements installed on a project, they are composed to an increased risk of post-installation damage. Common issues can include impact from moving machinery, accumulation of dirt and debris, and increased site traffic within the wall zone of influence. The zone of influence of a retaining wall refers to the area behind the wall where changes in ground conditions may affect its stability and performance. The zone is critical when assessing the impact of surcharge loads, such as structures or fill material, and must be carefully considered in the design to ensure the wall can safely withstand these imposed loads. While both suppliers and installers follow established quality procedures during the installation of panel retaining walls, the risk of damage to the product remains once installation is complete. The example shown above demonstrates a roller compacting soil after the retaining wall contractor has finished installation. This activity presents high risk of cracking to the concrete panels, which may ultimately compromise in structural integrity and lead to potential retaining wall failure. So minimum embedment. One of the most significant risks associated with sleeper retaining walls is installation non-compliance related to the minimum embedment of sleepers into the posts. Across multiple projects, we regularly observe installations that fail to meet this minimum requirement, often resulting in costly rectification works. In such cases, replacing the panel system can be a more cost-effective solution due to the integrated lifting points. By contrast, removing individual sleepers typically increases the risk of product damage during rectification. The frequency of these rectification issues has increased to the point that a growing trend is emerging within the market, whereby engineers are now specifying a minimum of 150 UC posts, therefore having a bigger face area to reduce the risk of non-compliance with embedment. Product quality is essential in the construction market. It directly dictates customer satisfaction, brand reputation, and long-term profitability. High-quality products create trust, differentiate brands in crowd markets, and foster positive word of mouth, while poor quality leads to wasted resources and lost customers. Concrete sleepers offer superior longevity, immense structural strength, and high resistance to rot, termites, and fire compared to timber. There are low maintenance preventing warping or splitting, and often modern aesthetic options. While initial costs and installation difficulty are higher, their durability offers long-term value. So how are they made? Here at Austral, the way we do things is we start with a mold prep into replacement, concrete casting, curing, mold stripping, and then back into mold prep, and the cycle goes on. Austral masonry concrete sleepers are manufactured to AS 3600. All reinforcing bars used for our concrete sleepers are compliant with AS 4671, and we manufacture and sell products to certified ISO 9001 quality management system. Here's a video of how they are made. So here's some examples of some poor quality made products. Example A shows the correct location of the reinforcement bars. If you look at example B and C, you can see the location of the bars for the reinforcement are not the same throughout the concrete sleeper. Therefore, increased risk of quality issues further down the track. So why Brickworks? Brickworks is 100% Australian owned with manufacturing facilities across all states. We have a strong focus on sustainability and continuous operational improvement. We've made significant investments and set ambitious targets to further reduce our environmental impact. We're passionate about collaborating on your projects, learning your vision, and bringing them to life. And our team is committed to supporting you every step of the way. At Brickworks, our focus is creating beautiful, durable products that stand the test of time. We are globally recognised as a leader in quality building products with brands that lead through style and product innovation. We're an active member of Australia's vibrant design and construction community. We value ongoing collaboration and dialogue. Your feedback helps shape the development of new products and services, ensuring we continue to meet evolving design and performance needs. At Brickworks, we're dedicated to building greener, cleaner, and more sustainable future. We've achieved a 50% reduction in Scope 1 and 2 emissions across all Australian operations, and we're targeting a further 15% by 2030. Currently, 11% of our manufacturing energy comes from renewable sources. Our ranges. Our concrete sleepers come in lengths of 1.2 metres, 1.5, 2 metre and 2.4. Whilst our panel systems are 2 metres long, come in what we call a 2-gang, 400 high, a 3-gang, 600 high, and a 5-gang, 1 metre high. Our concrete is poured at 40 MPa and it's cured to over 50 MPa. We have a design life of 60 years and a 35-year warranty, which is currently being reviewed to increase to 50 years. So thank you for having me today. Really appreciate your time. Hopefully I can assist you on any projects in the future and look forward to working together. Thank you.
Thanks so much, Adam. Well, now it's your turn to get involved, our audience. So a reminder to questions via the chat box, and don't forget to let me know who your question is directed to. A big thank you to everyone who did submit questions while registering for today's webinar. What I might do is I might start with some of those first, and then I'll jump into some of the live questions. So, Bert, I'll bring you back into the conversation. We had a question which came through from Victoria, and their question is, what is the recommended geotechnical design method? And then they've got Broms or Ivy Hawkins, if I'm pronouncing that correctly.
Okay, I have to admit I'm not familiar with Ivy Hawkins, so I'm not the fountain of all knowledge. I am a supporter of Broms, and I tend to use that one. But of course, I've said I don't know about the others, so it's a case of admitting that. But at the same time, Broms is a well-established method, admittedly since the 1960s, and has proven itself. It offers a lot of, shall we say, versatility of being able to also account for deflections, whether it's fixed free end, short or long piles, and it has that as part of the methodology. So Broms is my way to go, but it's probably because I'm a bit one-dimensional in not knowing much about the Ivy Hawkins. I hope that gives you a partial
worries. Thank you for that. Adam, I've got a question which came in from Krishanu from New South Wales, and it was around construction cost comparison. So they're very interested in understanding the comparison between base of block retaining wall versus concrete sleeper walls.
Yeah, so here at Brickworks, we supply both base of blocks or masonry blocks, concrete sleepers, dry stack retaining wall systems. And there's a current project we got going in the Hunter Valley. The first 2 stages were done in standard masonry block work. The next stage, we've been working closely with the client and the civil contractor and have moved to the project to concrete sleepers. For material costs, your base of block system is overall cheaper. But when it comes into play for cost savings is the efficiency of the installation of the concrete sleepers. So on the next stage, which is about 5,000 square meters, we were able to save the client about $150,000 in efficiencies over that quantity. So where we see the value and the customers are seeing the value is around the installation times of concrete sleepers versus the cantilever walls of the masonry system.
Awesome. Thanks, Adam. But I've got a question from yourself, and it's from a viewer in Victoria. And the question is, when is it safe to assume undrained cohesion CU in clay soils for the design of board piers? And when should cohesion be assumed to be zero?
Okay. You should not be using the CU undrained for long-term conditions. CU, by definition, represents a short-term condition, and of course, your wall is for a long-term condition. So you should be looking at effective stress conditions. There are two different approaches: a nominal C-dash, phi-dash, but the C-dash represents what is called a constant volume, a reduced, not the ultimate peak value, but a reduced value for what is called softening with time. And that's which is a normally small value, 2, 5, 10 kPa, say. That's a cohesion, but it represents a softened value, or in technical terms, constant volume value. Now, the friction angle is what should be used in long term, because and you can actually use with a C dash of 0 and a phi dash value on its own. Now, this has been, I'll try to make this short, but basically the Syria a document from almost 1984, so that's 40 years ago. It had a different approach, what is called a type A and type B, meaning that when you use a phi dash only without a C, you're allowed to use a lower factor of safety, say of 1.2, versus if you had used a C dash phi dash, which is called a method A, you use a higher factor of safety of, say, 1.5. It depends on what the sort of methodology you use. I'm just throwing out this sort of factor of safety approach. But you see, what happens is you have to allow for how your risk, and if by putting C dash as 0, then you're allowed to use a lower factor of safety. It's that in a summary fashion, but CU is certainly a not recommended approach.
Thanks, Bert. One of the questions, and I will move into some of the live questions because they're coming in thick and fast. Dougal's got a question. Is there a rule of thumb for smaller residential retaining walls as to when we need to get slope stability analysis done?
I guess I assume that question is for me.
Yes.
As a general rule, if you're near waterways, soft ground, previous landslide prone area, or if there's a lot of sloping ground in front or behind the wall, if anything exceeds 10% slope in front or behind the wall, you should really be looking at the typical active and passive pressure system does not really fully apply. So it's near flat to up to roughly 10% slope in front or behind the wall. But if there's a soft, even firm ground, you need to be aware of that for slope stability, global slope stability issues. Because sometimes that sloping ground provides a pressure far higher than just a simple horizontal pressure. It can almost double or triple the pressure than if you with a given height, simply because the ground is sloping. So be aware of that, and that's when you should be focused on global stability for also tiered walls.
Thanks, Bert. Sorry, Bert, I've got a few technical questions for you, so bear with me. Another question has come through live from Richard. So hello, Richard, who's watching. Could you say a bit more about ignoring now 0.5 HS for passive zone? Is this only for SLS or also ULS? In Adelaide, this would be 2 meters deep. So I hope that makes sense to you, Bert.
Yes, he's talking about what is called serviceability limit state, SLS, and ULS, ultimate limit state. And Adelaide, especially, has, I guess, highlighting the issue of expansive clays, which I highlighted in one of the bridge pairs that moved because of loss of passive zone. Now, I guess he's concerned about there's such a deep active zone in places like Adelaide where you have to allow for that. So you can't just start your analysis from the ground. You've got to allow for there is shrinkage and swelling, and that's the concern there. So I guess what I've highlighted is typically half the active zone. So if he has 2 meters of active zone, then half of that would represent the crack zone, and you should not bring that into your analysis as providing passive pressure. And that was highlighted in one of my slides. So roughly half the active zone. But I guess the concern there is especially places such as the active zone can be deeper. And therefore that goes deeper, that half the active zone, for what you might call the crack zone, loss of contact for the passive pressure. And I guess it does apply to both the serviceability limit state and ultimate limit state. I guess serviceability, the wall will deform more, and the wall deformation is a Adam sort of showed that or highlighted that. But what we have to keep in mind there is even the ultimate state, you need a certain movement before the passive pressure is mobilized.
Awesome. Thank you. I might give you a bit of a break, Bert, and I'll ask Adam the next question, but I've got a whole heap for you, so don't go anywhere. Adam, probably, I know you've touched on it with your presentation, but I always think it's good to kind of focus on what are some of the common product quality issues that you get through the installation process, because it's, yes, about the design, but it's also about the installation. So if you wanted to maybe just expand on that a little bit.
Yeah, thanks. So I guess with any concrete product, it's always forever curing. So from when it's poured to the curing process until when they're installed, it's always hardening. So the biggest ones we see are the cracking in concrete sleepers, and concrete does crack. You look at footpaths you walk on driveways, etc., and it does crack over time. We do have some quality systems in place where we use microfibers in the concrete mix, which we've seen great results on, and reduces that risk of cracking in the concrete sleepers. But I would say the biggest problem is just the installation speeds. Everyone's on a deadline to try and complete these walls, and you got to follow the procedures. And where the costs start to blow out is if you don't install it right the first time, especially with that minimum embedment of sleepers. So getting your post right at the start, there's nothing worse than pulling down a wall once it's been built. So that's where the costs blow out.
Awesome, thanks for that. Questions that I'll ask. The next one's around reinforced earth retaining walls don't have rigid reinforced concrete footing like the cantilevered retaining walls. How to estimate, or how they should estimate soil bearing capacity under MSE walls?
Okay, MSE's wall is moving away actually from this topic of sleeper wall. So it is a completely different type of wall. And I guess it's a bit off topic. I mean, it is part of walls, but reinforced soil walls respond quite differently, and there's a high bearing pressure applied. So it is a trapezoidal pressure, not the average pressure, and one has to allow for that tilting into that 1/3 front part of it. Now that sort of concept doesn't apply to sleeper walls in a stricter sense. So I guess I'm reluctant to expand more on that because it is a little bit off topic for
Fair enough. I definitely have a question which is on topic, and someone's asked, what is the maximum height of concrete sleeper retaining walls? And then they've gone just an approximate.
Over to you, Adam.
The largest wall we've designed, we're supplied to, is 4 meters in height. So I guess it's more of comes down to, I guess, the cost of the wall. 4-meter high wall, I think it was a 10 meter 310 UB that we had to supply for that job. So you're drilling big into the ground. Anything over that sort of height of 4 meters, we recommend moving to the MSE systems.
Thank you.
And
then there was, definitely
expand on that. A little technical aspects. When we talk about, Adam has mentioned the actual definitive height, but if we use that number 4 meters, for a wall to have what is called active pressure, it means, well, what the word says, active. It must move, and to go into active pressure mode from what is called an at rest, it needs roughly 0.5% of movement. So 0.5% of 4 meters means that your wall has to deform 20 mils. So Adam's number is, basically what it's saying is that if you go above that, you'll also observe something you may not like to see. It doesn't mean that it would reach what is called ultimate failure, but certainly from a visual point of view, it has deflected roughly 20 mils to be have that active pressure. So that's just a qualification of from a design aspects.
Thank you. We then have another question in a double wall, and I'm assuming this one's to you, Bert, and a double tier wall, how to consider the load applied from the upper tier to the lower tier. Are you able to provide reference, are you able to provide or reference the different offsets between the tiers? Thank you.
Not a simple question to answer without a bit of a diagram or illustration, but basically, Adam showed about the zone of influence for a wall and roughly twice the height. So for and that's just an approximation, but really, of course, to be sure, you should be about 3 times the height of the wall. So the setback should be of that order of magnitude, at least twice the height, so it doesn't impose additional load onto the back of the lower wall. But keep in mind that there is also that back wall has a passive pressure, so it also needs to not interact with the lower wall. So that twice the height for any individual height, offset or space is probably a first rule of thumb. That needs to be, well, more than that. For double tier walls, I tend to use actually just global stability analysis and then extract from the slices what the forces are individually. Not even though you've had your factor of safety, you have slices and what the actual forces on that particular element is, or that slice is, or that wall in this case within that slice. What is the actual force would give you the best, in this case, global stability and individual stability combined, but the minimum offset condition should apply, and that's minimum.
Thank you. We've got a question from Mohammed who's watching, and his question is, what soil parameters are used to design in clay soils, drained or undrained soil parameters? Should we assess the depth for both conditions?
Well, that question was partially answered in an earlier question where the undrained condition you should not use, and you should be looking at effective C-5- conditions. And when we're talking about clays, we're certainly talking about friction angles of the long-term, what's called effective drain condition, 25 degrees or less typically would apply for that condition. But again, not using the undrained condition, but the effective long-term condition.
Awesome. Thank you. Adam, we've got a question that's come in for yourself from Christos, and he's just asking, what was the spacing of Adam's 310 UB posts?
2 meter spacings between spacings of posts. Yep.
Awesome. Thank you.
203. Sorry. Yep.
Cool. And then, Bert, we've got a question that's come through. Can sleeper retaining walls be constructed along property boundaries without adversely affecting the adjoining ground within the influence zone? For example, staged excavation or installation of sleeper?
The answer to that is no. Once you install even the wall at the boundary, it does exert for its passive pressure resistance. I'm assuming, let's suppose you represent the upper part of the wall, then that pressure is being pushed into the it's affecting the ground in that property when it's at the boundary. And I guess if that person decides to dig a trench, for instance, that's why I mentioned about half a meter to allow for that, or an extra 10% each, then yes, your wall can be affected, but it's not, you rely on that ground in the neighbor's property being constant or not changing too much. So yes, there's an effect when you do that. So one has to be comfortable that they are not going to change that land too much directly in front of the wall, where you're relying on the stability of your wall on that passive pressure, which is in somebody else's land, if it's at the boundary.
Thank you, Bert. There was a question that has come through, Bert. How do we consider construction compaction vehicle loads in the design? Is there a clear approach for this? A surcharge of 12 kPa or 20 kPa will affect the design significantly, especially for sliding.
The fact they're talking about sliding means it's a generic question again, not specific to the Parliament's King Post walls, which we had under discussion, the sleeper walls. But point taken. Typically, you apply a 10 kPa, and I guess people are reluctant because you're adding on that pressure. The way to, of course, to not have to consider above that is to make sure that you're dealing with light compaction equipment, which I illustrated with the pressure distribution behind that. Because if you are using heavier construction equipment or compaction equipment, which can do the job faster and bring up the lifts quicker and all these sort of things, unfortunately, it does add that pressure. So it's a bit of site supervision that, or understanding within your footnotes of the drawings, that light compaction equipment only is required. And then a nominal 10 kPa, you can't do a 0 because there are so many variabilities for that. So a nominal surcharge pressure beyond that. But point taken that it does exert high pressure if you bring too larger construction compaction equipment for behind the wall.
Awesome, thanks, Bert. Adam, a question's come through around for Brickworks. Do you have design tables for sleepers?
Yes, we do. Sorry. We do have a generic table that we can supply to the market. If anyone wants to get in touch with me, I believe Engineers Australia can put up my email post this, and I'm happy to share that with them. And that sort of gives different tiers on different gradings of soil, and that we able to assist with the design of the system.
Awesome, thank you. Bert, and I know we're getting, I feel we're getting to the end of our questions. Our speakers are doing very well. There's a couple more which have come through with regards to, is there a way to consider or eliminate passive shrinkage serviceability issues?
Sorry, say again, to eliminate?
Is there a way to consider or eliminate passive shrinkage serviceability issues?
Uh, I'm not quite sure if there's a way to eliminate, I guess, reduce. I mentioned about designing for, in case someone wants to dig a trench in front of that. You could make sure there's a something that's not excavatable, you might say, in front of your wall, and because that's where your passive pressure is being derived from. Now, I guess there's an issue here that the wall must deform a bit for it to take up that passive pressure, and therefore, and there's more movement required for the passive pressure than the active pressure to be to occur. So, for instance, we design for passive pressure, but at the same time, to be passive, the wall must move a bit. Now, you don't physically see it because it's all below the ground, but it must undergo some movement, and that movement can depend on the site conditions or the soil conditions. Sorry, could be 1, 2, 3, 4%, 5% even for the passive pressure, but far less for the active pressure. So the point that's being made that you want to reduce that. It's how to reduce it. Honestly, I'm not quite sure. I'll have to admit that you do rely on someone not removing the soil in front of your wall, and whether you put something solid or non-excavatable at a concrete slab, for instance, so they can't excavate it. I mean, that's one way of getting around if you're considering or fearful of someone digging up in front of your wall, which would cause that loss.
Awesome. Thank you. We're coming to the end, everyone. I might be a bit cheeky and ask 1 or 2 more questions. There was a question which came through: is there a standard maximum step distance, or do we consider the lowest section design for the full height with the reduced load removed from the step above?
I think that question really goes back to the multi-tiered wall, which I already covered, that you needed that spacing of at least 2H minimum, so that the walls don't affect each other, the influence zone of the 2 walls. And that's twice the height step back as your minimum. And even then, it could still have an influence because of the passive pressure zone on the upper wall. So possibly even 3H, but I'm picking the number of 2H as your minimum to start your analysis with, and then try to see how that passive zone, you could extend just a 45, what it's called 45 plus 5 or 2, and extend it outwards to see if it touches the height of the lower wall as a first basis hand calculation approach. Of course, you could do through FEM, and you'll see easily if there's an interaction.
And then I don't know if I've asked this question, so my apologies if I have. There's a lot of questions. Can we double the sleeper panels for high retaining walls or high loads to get thicker walls? Would both skins work together structurally?
I'm happy to jump in there. Yeah, we do that regularly. We supply, I've seen up to quadruple thick panels. I guess it pyramids up as it goes up the wall. So 4, 3, 2, and then 1 as it continues, to give it that extra thickness, especially down at the bottom end of the load.
Awesome. Thank you. I'm sorry, I've just had a question come through. I've got to ask a question about construction applications specifically for compaction equipment. I feel like I asked that one. Was that? Oh, so for temporary structures, when would you consider the use of drain conditions once the excavation has taken place? Can you assume long-term drain conditions under the excavation dewatered level?
If you're going into dewatering conditions, etc., this is for a lot more considerations, and we did not talk about water conditions and the temporary conditions, which could, if they are trying to do some dewatering. I'm not quite sure if it applies to this particular wall, because you'd be more concerned with continuous walls, so that sheet pile, to prevent water from entering the excavation. if you're concerned about water and dewatering, etc., because of course these sort of walls, water will pass through. It has a natural drainage to some extent. There would still be required some drainage behind it, but it does have its own little inherent drainage system, these sleeper walls. So specific to sleeper walls, I'm not quite sure the question is directly relevant, but it's a very real case for continuous type of walls. And the issue of whether it's how long you have, well, that's the piece of string sort of question. In a clay, you may have some time. In a granular material, sands, gravels, it's pretty much instantaneous once you stop your dewatering system, because I guess that's what it's called, high drainage materials. And I hope that partially answers the question, but it is deviating away from the sleeper and post walls.
Awesome. Look, I might wrap up our Q&A with that one. So a huge thank you to both Adam Ransley and Dr. Bert Look for their time and input today. I'd also like to take the opportunity to thank Engineers Australia's industry partner, Brickworks, for their support. If I could ask everyone watching, if you don't mind completing the short feedback form, which is linked in the description box below. You know, that feedback really does help us to improve and plan future sessions for you. A big thank you to you all for joining us today, and we hope to see you at our next Industry Partners event. Good afternoon.